We know from long-duration astronomical images, such as those produced by the Hubble Space Telescope, that digital cameras are sensitive to ionizing radiation. This HST image is littered with cosmic ray hits, although the long streak was left by a passing satellite. Recognizing this ability, we have developed the RedStar system, a technology to detect the telltale image artifacts left behind in a video stream by gamma rays emitted by radioactive sources. These gamma rays, here marked in red, appear randomly scattered across the frame and only last for a single frame. A simple detection algorithm is sufficient for a dark environment, but for a realistic deployment, such as this subway station concourse, something more sophisticated is required. Otherwise, the radiation signal will be swamped by false detections arising from the underlying picture and from transient effects of passers-by. The advanced algorithms incorporated in the RedStar technology deal with these problems robustly, reducing the false detection rate by a factor of 1,000. Points marked in blue or green in this sequence taken with our 3-camera prototype deployed in a Washington area metro station indicate potentially interfering hits which our algorithms reject. Only locations marked in red are counted. The RedStar algorithms work even in as challenging a situation as this exterior scene with a shimmering waterfall and silhouetted trees. But true radiation hits are generally retained, as can be seen in this sequence taken in the presence of a radiation field with a dose rate of 5.4 R per hour. In order to demonstrate the active functionality of the RedStar technology, we returned in March 2009 to our deployed system for a live test. The test was done after fair hours, so our team came prepared to simulate subway passengers. So weak was our radiation source that the only way we could get enough radiation near the cameras to register was to place it right up against the camera boxes. Here we see the source at the end of the long pole being transferred from the camera at the bottom of the escalators to the one above the fare machine just out of view to the right. During the course of this sequence, our system measured the background level. After the required time had passed, we moved the source again, this time up against the camera we are currently looking through. In under 30 seconds, the system reported that it had detected an elevated radiation level, in this case one with a dose rate estimated to be 10 to 20 milliAR per hour. We had successfully detected a radiation-emitting device in the metro station. A radiation source of the size the Nuclear Regulatory Commission deems threat level would be seen out to more than 150 feet. If you keep a careful watch, you can see the detected hits flashing in and out of view. Despite their infrequency, there are enough of them to far exceed the number expected on the basis of our prior background measurement. To highlight the hits, we will pause briefly after several and indicate their location. Watch for the red squares, as here just to the right of center, for they can occur anywhere. Here hits are seen against the back wall, left of center above the railing, at top center, and again to the left above the railing. Further development work is ongoing, but what you have seen demonstrates that the RedStar technology is ready for deployment to an operational environment and capable of screening broad areas for dangerous sources of radiation.